All right, on to the use of conservation of energy in terms of power and efficiency. So remember, the energy can neither be created nor destroyed in the universe, only converted or transformed from one form into another. So if we have a transformer and we say that this transformer is an ideal transformer, that 100 joules of energy input should equal 100 joules of energy output. And in reality, that doesn't happen. But let's just use that understanding at the moment to see if we can sort of use our equations to come up with some various other equations to describe the relationship between voltage, current, and power, and the number of coils, right? So if you recall the transformer equation, the transformer equation is that the primary voltage over the secondary voltage is equal to the primary number of coils to the secondary number of coils. And so we've got a relationship here in our transformer equation between voltage and number of coils. Well, if we think in terms of power now, power is just a way of measuring energy. So power is the energy occurring each second in a circuit. And I guess we could say the power in the primary coil is equal to the voltage in the primary coil times the current in the primary coil. So the power is equal to the voltage times the current. And if we're focusing on the primary coil, this is what the equation would be. If this is an ideal transformer and we get 100 joules in and 100 joules out, then the power in the secondary coil would be this. And since there's no energy loss, the energy in is equal to the energy out, then these two will be made equal to each other. And so therefore we can combine those two. The power, or I should say the power going into the primary coil, which is the product of voltage times the current, is equal to the power coming out of the coil, and it's voltage times the current. So we have an equation here that relates voltage and current. Here we have an equation for voltage and number of coils. Can we now find another equation that relates the current to the number of coils? And the answer, of course, is yes, we can. Right? The old show, can Bob the Builder, can we build it? Yes, we can. Well, can we derive an equation? Yes, we can. All right, so what we're going to do here is we're going to rearrange some equations here and substitute them in to come up with a third equation. And to do that, I'm going to need a bit more space. So I'm going to rub this out and I'll be back in a sec. Okay, so what I've done is I've just gave us a bit more room, working room, and I've put our equations up on the right hand side here. So we've got our transformer equation, which shows the relationship between voltage and the number of coils. Then we had the idea of power, and remember we said that power was equal to voltage times current, and that we had power of the primary coil, voltage times current in the primary coil, was equal to the power in the secondary coil. And so we have a relationship between voltage and current. Now what we want to do is we want to use this understanding of power for each the primary and the secondary to then sub into here to see if we can get a relationship between number of coils and current. Okay, so let's see if we can do that. So I'm just going to give us a bit of room, a bit of working room, and so we're going to do the primary current here, the primary coil I should say. So the primary coil and the power in the primary coil is equal to the voltage in the primary coil times the current in the primary coil. Then, well, it's a bit squishy, but power in the secondary coil is equal to voltage in the secondary coil times the current in the secondary coil. All right, so what we want to do is make V the subject in both of these. So let's make V the subject. Now we've got V the subject, we're going to substitute the V's into here. So it's going to look a little bit messy to start with, but it's going to get better. All right, so instead of Vp, I'm going to put this. So it's going to be P over Pi, so that's our V, divided by our Vs equals, and then now I've got, I need to substitute the Vs in, sorry, getting carried away. So our Vs is our power in the secondary coil divided by our current in the secondary coil, And then of course now we have our number of coils in the primary, number of coils in the secondary. And so let's clean this up a little bit, because we've got a fraction divided by a fraction, so of course that's the same as timesing by the reciprocal. So let's write that, P over IP is the same as timesing by the reciprocal of this, so IS divided by PS. Now the power cancels out, because if you remember, in the ideal transformer, the power going into the transformer is equal to the power going out. So pretty much that's the same thing, so the power cancels out. What that means now, of course, if we rewrite this, the numerators times together, so we get just the IS divided by IP, right, equals NP over NS. And so here now we have a relationship between our current and our number of coils. Current and number of coils. Now what do we notice about this? Well, if we have a look over here, the primaries are both in the numerator here, and the secondary is in the denominator, but here it's switched over. Okay, so that's only the slight difference there. But now we've got a relationship between all our variables depending on what you have in the question. We've got the transformer equation where we've got voltage and number of coils. We've got power equation where we've got no number of coils now, but of course we've only got voltage and current data. And then we've got this equation here which relates the number of coils to our current. And so this concept of conservation of energy is very, very important with transformers, because you can't get more energy out of a transformer than you put in. And so if you have to have a step up transformer, if you're increasing the voltage, then you have to have a trade-off. Something has to be given, and that's usually the decrease in current, right? Because they're inversely proportional to each other. So as you increase the voltage, you decrease the current that's coming out of the secondary coil. And of course this is all assuming for ideal conditions, and we're going to find out in a second that with real transformers we have lots of energy losses. It's not as pretty as this. But here are our three equations that you can use. In terms of HSC, we've got this one here that's on the data sheet, and we've got this one here that's on the data sheet. I don't think that one there is on the data sheet. So you can derive this one from these two here if your only unknowns are current and number of coils. All right, that is conservation of energy with transformers and the three equations you can use to find the unknowns depending upon what you have in the question. See you in the next video.